A light ray is refracted as it travels from water into flint glass. The path of the light ray in the flint glass is shown in the diagram below. Using a protractor, measure the angle of refraction of the light ray in the flint glass. Okay, so this is a refraction problem. We have a light ray that's traveling in water, and then it goes into a different medium. It goes past this interface into flint glass. So depending on the relative indices of refraction for water and flint glass, it's going to either bend toward the normal or away from the normal. So the first thing they're asking us to do is measure the angle of refraction of the light ray after it passes through the medium, from one medium to the other, in the flint glass. So they want us to find this angle. So I'll call this theta of glass. And we can just measure that. I don't have a way to do that with a protractor on the computer, so you'll have to take my word. But I measured it on paper, and it's 37 degrees. So that one you would do with a protractor. But, okay, and the other thing that's really important to recognize here is that when you're doing these refraction problems, you want to measure theta, the angle, between where the ray actually goes and the normal. So we're measuring it against the normal. It's tempting to measure theta against the what would be the horizontal axis here, and it makes some sense to do that in the sense that it defines the same angle. I mean, if this is 37, then this must be 53. But because of the way the equations of Snell's law are set up, and that's where we're going next, it's important that we're measuring it against the normal. Okay, so try to remember that. Now they want us to calculate the angle of incidence for the light ray in water. So before the light ray got to this point where it was traveling through the glass, it was traveling through the water. And we can calculate what the angle was against the normal of that light ray. But before I draw it, I want to get your intuition about whether it should be closer to the normal than it is when it's in the glass, or further away from the normal. And to do that, we got to look up the relative indices of refraction for water and flint glass. So if you go into your table of values, you'll find that the index of refraction for water is 1.33. That's N for water. And the index of refraction for glass, flint glass, I'll just put G for now, is 1.66. So when you have a refraction problem where it's going from a lower index to a higher index, does the ray bend toward the normal or away from the normal? Well, when it's going from lower to higher, it bends toward the normal. So that means before this moment in time, it was further away from the normal. So I'm going to draw it like that. So this theta for the water, is going to be larger than theta for the glass. Theta water is going to be larger than theta for glass. Because the index is going from lower to higher, the light ray bends toward the normal. If it was the other way around, if we were going from glass to water and the index was going from higher to lower, it would bend away from the normal. And so we would have made this angle even closer to the normal here. Okay, so it's really important that you understand that, at least on an intuitive basis, before we go plugging it into an equation, that this is what's happening. And also, it's probably going to have us draw this angle with a protractor, and I've just estimated it there, so I have no idea if it's going to be exactly right. So you'll have to just forgive any inconsistencies with that angle. Okay, now let's do the Snell's law calculation. They want us to find that angle of incidence. That's theta W that they want us to find for the light ray in the water, and show the work. So the equation for Snell's law is N1, well actually I'm going to use the symbols for water and glass. So N water sine the incident angle in the water equals N for the glass times the sine of the incident angle with the glass. And we know these indices of refraction, and we know the angle in the glass, we just don't know the angle in the water, so that's what we're going to find. So let's get sine theta W by itself, and at the same time let's make the substitutions on the other side. It's going to be NG over NW times sine theta G. So N for glass is 1.66, and that's times sine of 37 degrees, and that's all being divided by 1.33. So let's find out what that equals. Where's our calculator? We have 1.66 times sine of 37. That doesn't look right. I think we're in the wrong mode. Yeah, we need to be in degree mode. So can we just go over to degree mode? That should do it. And now we can get out. So again, it's 1.66 times sine of 37, and then divided by 1.33. So we get 0.751, and now we want to find what theta w is, not just sine of theta w. So to find theta w, we do second sine, inverse sine of that number 0.75. We get 48.7, so we'll just say 49 degrees. So this was 0.751, and then theta w was, why don't we just say 49 degrees? That's close enough. Okay, so now we have theta w equals 49 degrees. I'll put that up here. So hopefully I did that reasonably accurate. If this is 49, then this part would probably be 41. That could be. 49 degrees. And now, using a protractor and a straight edge on the diagram, draw the path of the incident light ray in the water. We did it first because we wanted to get that gut feeling of whether it was going to bend toward the normal or away. So we already drew our line. Hopefully it's okay. And identify one physical event other than transmission or refraction. Obviously this is refraction. I hope that's relatively clear by now. That occurs as the light interacts with the water flint glass boundary. So as it goes past this boundary, what else happens besides refraction, besides this phenomenon that it bends toward the normal? There are other phenomena going on. The one that's most, well, actually there's three that usually kind of go together. There's the part that goes through, which is refraction. Then there's the part which just gets absorbed by the boundary. So you might say absorption. Absorption. And then there's whatever doesn't make it through or get absorbed by the boundary comes back out. Maybe that would be coming out, that would be reflection. And there are other possible answers as well, but these are the two that I think of because the three kind of go together. When you have an incident light ray, it can either reflect, absorb, or refract as it goes through. So hopefully one of those two will stick with you, and that should do it.